Okie doke. Hi, everybody. We are live. Welcome to class. Let's talk a little bit about where we are. In this class and the one on Wednesday, we're going to talk about what actually happens, what's some of the things that happen, or start to think about what happens when your query actually gets executed. And let's talk about where we are. So as we announced, we'll have the quiz and class on Friday. It's not something I think you need to study for, particularly if you've been doing your homework, especially up through homework 3. It's basically SQL practicing. Trying to get homework 4 released tonight. It's pretty simple. Don't necessarily think you should get in the way of to get too distracted by it if you're practicing your SQL, but this is practice in UML and practice in relational excuse me, relational algebra. Homework 3, I think about half of them are graded at this point. I did notice that we don't have a 100% of the submissions are required. And I know about a few people who've talked to me about catching up and that they're late because they registered late and things of that sort. But that's a worrisome sign, especially because that's what you're going to be tested on Friday. So not only are you behind, it might catch up to you when you hit the quiz, which would be a shame. It's likely, as we're building on the material of, this is how to code SQL this is how SQL is executed as we're building on that. And the next homework that follows, homework 5, you're going to get further and further behind, and that's dangerous. So if you're in that kind of shape, give us a holler, give your TA a holler, give me a holler. We'll see what we can do to get you back on track if possible. I know there's a lot of other midterms going on at the moment, so maybe it's just a matter of you trying to juggle your priorities. Anyway, let us know if we can do anything. Homework 5 will follow. That's a fairly substantial homework. It's also a couple weeks worth of work, and it really is more work than any other assignment that we give you. It's also a little bit more free form than some of the other assignments, and it can be pretty challenging. The TAs have all gotten through it alive, and they'll help you get through it, but get ready. That's also where teaming may help to figure out how to break up the assignment so that you can team up on it, but that might be a priority for those of you that homework 4 due, Shannon, is going to be due the following Monday. If we get it out tonight, which I'm hoping, it'll be due for the following Monday. I'm going to look into that right after we're done with lecture. But it should be ready to go, but I didn't hear confirmation from one of the TAs involved. So, okay. Okay, so homework 5. And with homework 5, this doesn't affect you, it affects me, but I'm a person in this class of interest. But it might involve juggling some of the priorities or some of the order in which I was planning on presenting things. I'm working that out at my end. I don't think it's going to be a big deal. You probably will never notice. But I will revisit the reading assignment and make sure that I have some of that reading available for you, and I'll make that assignment maybe Wednesday. I just checked earlier this morning. I checked the Azure account status. Most of you are in pretty good shape. There are a few people that have burned through a good portion of your money. Well, the average person, the median person, looks like they've spent $4 or $5 out of the 50 that's allocated. But there are a few of you that are in the 20s and 30s, and I'll have to see what I have to do at my end to get you some more money, because we don't want you running out of money in the middle of a test like Friday. Okay, So that's that. And the other capacity issue for us has been, I record the lectures locally. Afterwards, they get converted by Zoom. Those recordings we put to Canvas rather than the website for privacy reasons. Sometimes there's some of you guys are identified sometimes. And when we put them into Canvas, there's a limit on space in Canvas. So we're beginning the process of archiving older recordings to the Panopto folder. There's 10 or 12 there up in Panopto at the moment. And they're a little bit difficult to find, but they're all there. And I'm working that out for you. But I think the first week's worth of, that's old history, really. You're way, way past that. So I don't know that you necessarily need to go back to that stuff ever. Probably want to wipe it off your brainwash it, or whatever they call that. But anyway, just mentioning that. Okay, so let's talk about where we are in the class and where we're going to go over the next, I would say, 4 weeks. So we're going to pivot from, right now we've been discussing SQL in very abstract terms. It's a mathematical language. It's a declarative language. It's akin, it's isomorphic with relational algebra, set theory, except that's the sets. And as we talk about how your queries actually are executed, we start to deal with the fact that this is a physical database. It lives someplace. It's a process. It lives on disk. The data's on disk. All of those. It has backups. It has recovery modes. It has all of those aspects that are going to start to become relevant as we talk about the execution of your query. So we're going to be looking today at the optimizer and some basics about it. And I'm also going to talk a little bit and put it in context about the architecture of the database engine itself, in terms of how it's situated, client server, things of that sort, some perspective on this. If you're new to this area, then this is probably the first time you've encountered something like this. And so I expect that to raise a few questions. Wait a minute, before let me finish this introduction, and then I'll go and check on your questions. And then we're going to be looking at transactions. And I'll introduce transactions today, but just introduce them. But that has to do, well, we'll see what that has to do with when we get to that area. And that's partly what we're going to cover when you do homework 5. And then we're going to get into physical database design, basically indexing, use of indexes. Okay, where can I find more detail regarding details on Friday's quiz? There's no more detail than what I told you. It's a quiz. It's on SQL. It's practicing SQL. Tanish answered that. Thank you. Yes, you'll continue to be able to use locally downloaded database instead of Azure. If you're happy with that option, we're certainly happy with that. The quiz is 90% practice of SQL, specific SQL. Yes, you could practice some of those questions. It's a quiz, it's a midterm, it's a quiz. If it were longer than 45 minutes, I would call it a test. Will the quiz be covering topics such as RA? No, just mainly SQL. How many questions? I don't know, Haley, but you'll find out on Friday. Sorry for the suspense, but you'll all stay tuned. You'll all find out. All your questions will be answered on Friday. Okay, so what we're going to talk about today is query execution, some beginning notions of cost estimation. I don't know how far we'll get into that today. But we'll finish that up on Wednesday, and we'll be talking about basically how joins work. That's more complicated than mere table scans. Once you start getting joins, then performance gets to be more of an issue. Okay. Oops. This keeps happening. I am sorry about that. Okay, so So you wrote some SQL queries. Basically, SQL tells the computer what data and set operations you want to perform on that data, what data you want to select, and what set operations you want to perform on that. And the database management system itself needs a way to execute this query, and this is known as the execution plan, the query plan. And the way this looks schematically is your SQL is parsed. Once it gets through the parser, it's translated internally into relational algebra, or something that looks very similar to relational algebra. The explain graphics that I've showed you over the past couple weeks when I was doing some demos, that's somewhat very similar to relational algebra. And what we need is relational algebra alone is not enough to describe the execution. We actually need some algorithms, some understanding of the physical plan is needed to create the full execution plan. And this is because the physical organization of the data stored on disk factors into the plan optimization. That factors into what the optimizer does. So there's our picture. There's some data out on the right here. It's ones and zeros, so I guess it's binary data. The RDBMS is taking your SQL and translating it into something akin to, close to relational algebra. And in order to find the data, there's some stuff that has to happen. So we're going to call the SQL into simple relational algebra, the logical plan, and now we're going to be discussing the physical execution plan, because there's lots of ways that you can take a given logical plan and generate physical plans to do it. So a good example would be a from statement that references 3 tables. There's nothing in the from statement that you're going to be joined. There's nothing in the from statement that specifies the order in which those 3 tables can be joined. So if you think about tables A, B, and C, the one plan would be to join A and B, and then to join it to C. Another plan would be B and C, and then join it to A. Another would be A and C, and join it to B. All 3 of those options would execute the same logical query. So that's how multiple execution plans get in physical plans get generated. And what the optimizer does is pick the plan that it feels minimizes the cost of execution to get you the data the fastest way that's consistent with your query. Okay, just checking to see if there are questions. Okay, so one of the things that the physical plan, the optimizer needs to know when it evaluates these physical plans is it needs to understand the table size. And this is number of rows and how they fit into blocks on the disk. So because your data is blocked up, and actually, as we'll talk about, the minimum size of a request to disk is a block. So the size of your rows, the size of the block, that determines how many rows you would have per block. So that's data that the optimizer needs to know. It needs to know the cardinality, number of data rows, basically, and of course the row size. And we've been experimenting mostly with varying length character fields in our data, but there are a number of variable length fields that are possible in a relational model. And there's even what they call blobs. Those of you that played with Azure SQL, we stuck all of our files in a blob. You could put images, you could stack a bunch of images in a blob, and these would be of variable size. I forget what the limitation on the size of a blob is, but it's fairly large to put into a table. So the amount of data that's there per row also could vary with these varying size fields. The other thing that the optimizer knows, which we'll get into in a few more weeks, is it actually understands what indexes exist, and it understands the distribution of key values in those indexes. Now, if you take something like a primary key index, which gets built for you when you specify primary key, those values in that index are unique. The values of the primary key are unique for each row of the table. That's why they're identifiers the way they are. So the distribution of key values of the primary index of your tables is pretty trivial. There's one for every row. But indexes for secondary indexes that are not unique, and we created one when we were playing with the flights database to index the origin cities and the destination cities, to build those secondary indexes. That's the kind of distribution of those key values that makes a difference to the optimizer. And we'll drill into that and how that works in a minute. We're not in a minute, in a few weeks. Right now, just understand those are the two things that we need to know. And in this class, the only thing we really care about is the table size, which is the number of data rows. We're not going to assume yet anything to do with secondary indexes, just primary indexes and equijoins and things of that sort, foreign key kinds of joins, okay? Okay. So cost estimation, this is it's an active research topic. People doing cost estimation involve many factors, parallel database, network, CPU cost. The cache is a difficult one. That happens to be an area that I'm very interested in. I've been interested over the course of my career, and pretty much the cache, the influence of the cache, which is enormous, is opaque to the optimizer at this point. So we're going to talk in the class about very general kind of methods for executing a query, but when we compare what we're talking about in the class to what actually SQL Server generates as a plan, and we start to look at a plan explained, you'll see that they roughly do this, but they go beyond this. So we'll explore some of the proprietary capabilities of something like the SQL Server Query Optimizer. We'll look at histograms that are kept on its distribution of secondary key values. We'll look at something of what it does on parallelization. But in this today and Wednesday, we'll be talking about very general solution methods. Okay, so we want the RDBMS is going to select the least cost plan. SQL's turned into RA. The RA generates a set of equivalent RA that become the set of physical plans. And then the optimizer evaluates each of the physical plans and then selects the least cost plan. So it's an estimated least cost, you don't really know. But the most significant cost factor, historically and still today, is the disk I/O cost. So if we just concentrate on the disk I/O cost, we are probably got it about 90% right. I will try to keep that easy. And I think it's just an example of, here's some SQL, here's some logical plans, here's my T, R, and S. You see I could join them in any order. I could join T and S first. I could join R and S first. I could join T and S. All of those would be possible logical plans that are equivalent for that SQL. So here they are. These are these equivalent logical plans, just executing the joins in any order. And that's right, relational algebra is an algebra. These join operations are essentially associative, so they can be done in any order. It is an algebra. I'm emphasizing that for some reason. Then from these, we'll get the generation of the physical plans. understanding the size of all these relations and whether there are keys involved, secondary keys involved, when you do these joins. And out of that comes the least cost plan, and that's the one that's going to be executed for you. Now, this process is taking place whenever you issue dynamic SQL, which is everything you've been doing. However, there are the compiler options, basically, where the SQL is pre-built, the plans are executed or kept in advance, and they're executed over and over again in a very efficient manner. Hopefully, unless the database changes, for instance, and then that old execution plan is no longer a good plan. So plans are kept around. Plans are stored, plans are remembered by the DBMS, and plans can be very complicated. We're doing relatively simple SQL work involving very simple kinds of databases. So the plans can get very, very complicated. I think I came across something in the SQL Server documentation that said once SQL Server got to the point where it found 2,000 or more plans that were equivalent, it stopped trying to enumerate them all, and instead would just have some heuristics that would go and try to find the best kind of plans, which makes a lot of sense because you could have a join and a join and a join and all these other equijoins that are occurring that we've seen, and they could be done in any order, and then depending on the one operation, which you might have 3 plans for, above that you're going to have another join or a with or this or that, and that could be done in any sequence on top of that. So it gets combinatorial very quickly. Okay. So to talk about what the query optimizer does, we're making some assumptions. The assumptions these are not necessarily the best assumptions, and I'm going to clarify them, that when I'm discussing this, I'm not necessarily making these assumptions, but maybe for you to think about it, it might be helpful to think about it in simpler terms than I'm familiar with thinking about it. So we're talking about disk-based storage, and we'll talk about a little bit about hard HDD, hard disk drive performance in a minute, because that is the biggest cost item is the storage. Over the past, I'd say 4 or 5 years, we've seen that solid-state disks, which are basically static memory arrays, like in your phone, that don't, those things that you plug in, those little cards, that kind of thing. Well, that's being made at an enterprise level and beginning the process of replacing HDDs because they're about 1,000 times faster and they're not that much more expensive. Most PCs, the PC here that I'm running, I don't buy this with an HDD anymore. It costs a little bit more, but I buy it with an SSD. So HDDs, hard drives, mechanical disks still have some cost benefits, but in data centers, we are seeing massive replacement of HDDs with solid-state disks. They have very different performance characteristics. What you basically have to remember is they are much, much faster. So Jonathan, who did these foils, he's got said that the idea is that the rows are stored on the disk in contiguous blocks. That's not actually true. Basically, allocations are done by the file system. The file system will allocate groups of segments on the disk when your application requests it. They are contiguous to the extent that they can be, but they're not really contiguous. And it doesn't matter at all with SSDs whether they're contiguous, because SSDs, their memory, they can be accessed randomly as quickly as they can be accessed directly. But hard drives are not quite that way, so contiguous is maybe important, but in fact, it's usually out of control of the database. That's responsible for the underlying file system. That's an operating system function. But anyway, reading from the disk is the main cost factor. In the case of an HDD, a hard disk drive, it's about 10 to the 6 slower than actual RAM access, getting to the data that's stored in memory in your computer. So that's a huge number, a huge number. And so when the database actually has to go off to disk and find the data, that's a very, very slow operation. And compared to the data being in cache, which is what happens to frequently accessed data. So cache is a major, major factor and is not built, it's opaque to the optimizer, it's not built into any of these cost models. Just checking, okay. As far as disk latency for SSD, instead of 10 to the 6 times worse than memory, say it's more like 10 to the 3 times worse. So it's 1,000 times worse, while access to hard drive is maybe 1,000,000 times worse. Microseconds compared to, or nanoseconds compared to milliseconds, nanoseconds compared to microseconds, something along those lines. So yeah, this is a little bit outdated and I'm not really thinking about it, but we'll try to keep it simple. Okay. So historically, because IO performance being so important, the DBMS themselves are optimized to obtain the best possible performance from these mechanical hard disk drives. However, increasingly SSDs are replacing HDDs in most data centers. They're not requiring it. SQL Server doesn't even know about it because it's transparent to SQL Server. But they're not only faster, they don't really require much optimization. The optimization is mostly about getting the data sequential on a hard drive, but SSDs, we don't really care. We are getting SSDs now that basically emulate hard drive functions. So they look to the operating system as if they're hard drives. There's a move afoot in the SSD community, what they call non-volatile memory, NVMe, that to have a native interface. And these native interfaces will be even faster because the SSD doesn't have to be forced to look like an HDD, which it is not. Okay. So what I wanted to do is step back a little bit and talk a little bit about the architecture of the database itself. So what we have in the computer, this whole box here is the computer. The inside of the computer, I guess, and it's got a bunch of disk drives that are attached to it. And at the highest level or at the lowest level, perhaps, is the operating system itself. The operating system includes a networking component. These days, that's TCP/IP, but TCP is changing a little bit. And read requests and write requests, SQL requests are coming in over the wire. It's a wire protocol. There's a wire protocol that SQL uses that you're using when you connect and you're using when you actually send data. And these requests come through the networking stack inside the OS, and they are forwarded from the networking stack into the application. Now inside the application, which I've drawn here, I've called it a process address space. It is a single process, but inside of it, there's a whole lot of execution threads. Let's call them, for the most part, they're worker threads, because they're worker threads that can take on any piece of work. And what happens is a read request comes in, it's stored as a work item. A write request comes in, it's stored as a work item, and then this dispatcher matches up pending work items with available worker threads and gets them to work. Now, there are also worker threads that are done internally that are used, for instance, a dispatcher thread, or we'll see that there's a thread involved in writing the transaction log, for instance, which I've shown here. So as far as reads go, here's a bunch of disks we're showing. This is a big database. The databases you're dealing with are not very large, but in the real world, they can get very large, which span multiple disks. And I'm showing here that they are blocked. The database is set up so that it only reads block from disk. It's very inefficient to read a disk a byte at a time. it's much more much more efficient to read blocks. And in fact, what the database does is it only reads and writes blocks. And what in your mind, you want to think about these blocks as being managed in a buffer in memory, in the DBMS process address space, memory that's accessible to each worker thread, and it's managed by a buffer manager, by a manager of some kind, a DBMS component that understands which of these blocks are free and which are occupied, understands for read requests that it's going to need to allocate some new free blocks, and they're going to become occupied, and understand when eventually the buffers fill up of which blocks in memory have been written into based on inserts or update commands that have come in, write requests of a general nature. Those would be flagged as dirty blocks. And they're dirty in the sense that they not only get written out, when they get written out, they have to be written out to the disk. And there's an additional level of data protection involved in something called the transaction log, where changed pages are written to the log as well. And we'll delve into that particular aspect of the way the database works when we start to deal with update requests, when we start to deal with inserts, and we start to deal with the idea of transactions. So for now, I don't want to go into detail about that aspect of it, but what you should know is that these are blocked reads and writes, and the blocks are the same size all through memory, which is effective from the standpoint that any block from disk can be anywhere in occupied buffers. And that's very flexible. So only blocks are read and written back and forth in the database. Questions about that, you guys? That seem fairly clear or no? You're happy to move on, huh? Okay. I don't see any questions. Okay. So fixed blocks. 2K, 4K, I'm familiar that IBM's DB2 uses 2K for index blocks and 4K for data blocks. At least they did 10 years ago, last time I checked. SQL Server actually uses a somewhat larger block. It uses 8K throughout. Everything, as we're looking at Microsoft SQL Server, everything is being done in reads and writes in 8K blocks. And buffers are allocated in 8K units, and blocks are put into them. So tables are stored on the disk. Indexes are stored on the disk. And we'll see what index structures look like in a couple weeks. And there's even a place for doing things like the temporary storage. In case you have a join where the data won't all fit in memory. We're not going to talk about them because that starts to get a little bit complicated. The disk is involved. Or you need to do a sort, and you need a place to store your temporary results. And they'll overflow memory. There's a temp database for that. The buffer manager is responsible for these blocks, probably calls them pages, or it's another way to think about them, but they're equal size hunks off of the disk that your data is actually placed into. LRU stands for least recently used. What happens is there is also information about not only which of your blocks in the buffer manager are dirty, have been changed, and still need to be written out to the disk. There's also information about, well, when was the last time that particular page was touched by a query? So that if memory fills up, the buffer manager starts to be out of space, needs to allocate some more, it can go through and find the least recently used buffers, and if they're current, there's already a copy of them on disk, so they can be removed safely and overlaid with new data. If they're dirty, that's when we need to make sure that they get pushed out to disk and also to the transaction log, and that gets a little bit more complicated. But if they're just read kind of pages, no reason, since they're backed up on disk, why you would worry about removing them if they haven't been used for a while. Seems like a good idea, in fact. LRU. LRU is used in buffer management in database. It's used the way paging works. It's used in many kinds of caches. So it's relatively simple and relatively optimal. On the transaction recovery log, I'm just mentioning this at the time. That's a file that's 100% right. Essentially, basically, it's going to contain before images of change pages and the change pages themselves, and periodically checkpoints that say, "Oh, this bit of work is done," and it's hardened on disk, and there's no reason to go back to me. But there is an ongoing log of what you've changed and what you've changed it to, if you will. Okay, so let's talk a little bit about, with that in mind, the way the database is deployed, the way it's built. Now, those of you that have installed a local copy of SQL Server and are running with that, you might get a little flavor of that. You might have noticed that it's another process that starts up. In the real world of production databases, these databases systems are so important and they're critical that they usually run on dedicated virtual hardware, dedicated hardware, which may be virtualized, maybe not, but dedicated. So that there's an operating system, and about the only thing that operating system runs is this one SQL Server process. That's pretty typical. Now, we don't do that in development. I run with a lot of things because I'm not really a server. But what we're talking about is talking about servers that are designed to support many requests coming in concurrently from around the world. You're all using your own local databases, but we could have had you all running off of the same database, for instance, and all of you could have had credentials and be accessing the single database. We don't want you to get in each other's way, and of course, your local database, it means you have no constraints on it. If you're running SQL Azure, that is virtualized hardware, and it might not even be a dedicated machine just for your SQL. It could be multiple SQL servers running on a single machine, but it's probably only SQL servers running on that machine, if it is. And relatively small ones up to very large ones, and very large ones, they are running on dedicated hardware that aren't virtualized for a little bit of extra performance. So the database is the server, and when you connect to the database, you're connecting via a client interface of some kind. There are command line interfaces. Most of you are using a GUI interface that makes that connection and sends SQL to the server and gets it back. And again, you want to be thinking about this in terms of scale. How do we go from the kind of database that we're looking at to the database that supports the transaction processing associated with, say, an airline reservation system? Since we're talking about flight databases, that might be a good one to think about in very relatively concrete terms. So think about if you've ever made a reservation for an airline flight, and you're coming in and you're basically contacting an application that is in turn contacting the database where they keep track of all this stuff. So we're going to start looking at how we would take this tiny little play database that we've been playing with, our flights database, but how you could start to extend it to make it into a client server application that would support, for instance, flight reservations. Now, that's called transaction processing, where requests are coming in from multiple clients, and those kinds of requests have to be dealt with in terms of their integrity. And we'll see that when we talk about transactions. But the thing to keep in mind there is that a request for a reservation seat on an airline, that means I'm the only one who can get that seat. And we don't want to have logic. We want to exclude logic that would allow someone else to reserve the same seat. I show up and there's somebody already sitting in my seat. So we need that kind of integrity and constraints around the database, and those are called transactions. Now, for very large production databases, they're actually clustered. There might be there are high availability options where there's a primary database. As that's changing, those changes are reflected somewhat later in time with some latency in the secondary database in the cluster. But this high availability means that if there's a problem with the primary database, we can cut over to the secondary database, and you'll hopefully never notice it. You might have to apply the last couple of transactions, of the last couple of updates, but we'll be able to, with that clustering ability, to be able to take over the workload, do maintenance, add some more stuff, add some more memory to this machine. Meanwhile, I'll be running my work. So now the most common kind of high availability option you're going to see in databases, though, might be clustering, but more likely is disk mirroring. When you're writing data to Azure, at least the way they used to do it, is they're actually writing data to 3 different disk mirrors. So that in case of you would maintain your data that you put up there unless 2 of those mirrors, all 3 failed at one time. Very large databases run in parallel. Where we get to later in the class, we'll be talking about how we could have multiple databases, usually that are geographically distributed, and how you could have a single request that would update multiple locations, database and multiple locations. We call that distributed transaction processing. And a final aspect of the way RDBMSs are deployed, if you're involved in a data science exercise, for instance, they might not give you access to the production database. They might instead give you access to what's called a data warehouse, a read-only version that's maybe not super up to date, but maybe it's refreshed weekly or daily from the current production DB. And the idea is, we'll see, the reason for this is to get your work off, because you don't necessarily need to be cluttering up the production database and messing around with the people that are trying to get a reservation through. We want to make sure that happens as painlessly as possible, so that they're coming to my reservation service and they're flying my planes, that we don't lose those customers and they go someplace else. So you might be doing data analysis on, how many planes do we need on this route, or what's the percentage of occupancy on all these different routes, so we can figure out where to move the planes. And you maybe don't need the most current data. You could that analysis is going to be based on yesterday's data or the past month's worth of data. So that'll be possibly in a data warehouse, a read-only data warehouse that's only periodically refreshed. Okay, so let me see what some of the questions are. Is the buffer basically the same as a write-back cache? Yeah, it's basically the same as a write-back cache. That's good terminology. I don't know where you picked that up from, Shirang, but that's about correct. I would say it's different than a deferred write-back cache, though, because the transaction processing element normally leads us to want to write sooner than we would be in many other caches. But yes, it's similar to a write-back cache, deferred writes. The write may not take place synchronously; it will take place asynchronously. The rest of you can ignore that. So let's talk about that. I don't understand Steve's comment, but that's basically it. So yes, your idea that it's a write-back cache is essentially correct. Okay, let's introduce the idea of I've been talking about them. Transactions mean something very, very specific in the database world. And they are known by 4 properties, I think because they make a nice acronym. But Jim Gray, who won a Turing Award for his work on transaction processing, he's the one who standardized, Bernstein and Gray standardized on this transaction terminology. ACID stands for atomic, consistent, isolated, durable. I'm not going to go into all of that yet, but the idea of atomic, let's start with that. The idea of atomic is that whatever changes you want to make, where I'm going to assign this particular seat to you, and remove that seat from its being available to others, that has to be done as one atomic, logically one atomic operation. And if it's not done in one, it's a unit around it that says it either works or it doesn't. If it works, fine, change the database. If it doesn't work, any pieces of it, you back out all the changes. So that's the function of the transaction log, keeping track of changes that have not necessarily, as part of a transaction, that have not necessarily been applied to the disk yet. So that's one aspect of it. We'll deal with transactions in another, starting next week. So let's not go into that in too much detail now. Let's go back to talking about the disk and query cost the cost estimation that goes into queries. Whoops, I'm running out of time here. So as we said, the disk storage is allocated in fixed size blocks. SQL Server happens to use an 8K block size. The database server is maintaining a buffer pool, and this buffer pool serves as a disk cache. And in fact, for instance, if you look, show you where it is, but this least recently used algorithm tends to be used by caching. And actually, there's a SQL will report that statistic. You can get the age of the least recently used buffer currently in the pool, and you use that age to figure out if you have enough memory, maybe define more or something like that, physically allocate more. Okay. We're running out of time. Let's talk a little bit about the hard drive. The SSDs are much simpler because they really only have a data transfer component. But there's a picture. It looks like it's of a hard drive, and you see it spinning. If that's showing up in the video, I don't know that you're seeing. And you see an actuator arm that's moving back and forth. And actually, the disk is usually is a stack of them, and there's a stack of actuator arms that are top each of the disks. So it's usually a stack of disks. And each disk is physically organized into tracks, which is data that goes around each of the disks. Like, well, people don't see long playing records anymore, but tracks. So they're physically located in tracks. Now, and then bits, our magnetized bits, are located on the surface of each platter in where a track is supposed to be. And the key is to position this read-write arm, a mechanical device, so that it finds that particular track. The track that you're looking for, you're only particularly getting a sector, one portion of the track, and that you're reading and writing is where your block actually lives. The blocks are logically formatted by the operating system when you do a disk format. And then the database itself then puts its own logical block on top of the file blocks that it gets from the OS. But so what's physically being read from the disk are these disk sectors. Now, if you think about the way bits get recorded on the device, they're going to be spaced around each of the disks. And you can imagine that the disks, the tracks that are much closer to the center of the disk versus the ones on the outside of the platter. Typically, disks are recorded on maybe 2/3 of the magnetic surface that's there. That the outer tracks are going to potentially contain more data. You could use what's known as constant bit density, and then every track, because every one as you go out from the center is larger and larger. If you use something like constant bit density, the outer tracks are going to be able to store twice as many bits. Constant bit density is a little bit complicated for the operating system to figure out. So they're usually they're constant in the disk is usually recorded in bands of tracks, so that inner bands have less data, outer bands have more data, and maybe it's not quite 2-to-1, maybe it's more like 2/3, but outer tracks contain a lot more data. And that means that you can read the outer tracks faster because you can get more data off of the disk in a single revolution. Once that you have a seek operation that's moving the arm back and forth, and it's moving to a specific location of all these tracks, and then you're waiting for the the disk to rotate. There's some factor of rotational delay. And then you have a data transfer function, which is a function of the speed of the disk and the bit density at that particular layer. So that's how hard drives work. The key is that once you get to a particular track, then you could read sequentially in that track much faster than you can do the mechanical seeks. And you're no longer waiting for this rotational delay. So there are advantages to sequential disk reads. And some of what we're going to be looking at is talking about how that might get built into the optimizer, the fact that reading the disk sequentially is faster. Again, with SSDs, this is just a memory array that's configured to look like one of these disks and tracks and sectors and things of that sort. There's no real benefit to being sequential or random. But the optimizer might not know that. Okay, so we have tables. This is the final slide we have time for, is that the tables are stored as file segments. And there's two ways you can store the data. And you can store it in a heap where it's unsorted tuples, which is basically what we're going to talk about in this lecture. And they're allocated in contiguous disk segments, although disk segments are not necessarily contiguous with each other. They're wherever they can find them on the disk. But another way that your data could be stored is sorted. And there's a sort key, and we will look at that when we talk about physical indexing in a future class. So that is, what is 8K? 8K means 8192. That's number of bytes, sorry. 1024 is 1K, and we're counting in kilobytes. Okay, everybody. That's a bit to absorb for everybody. Why is it a heap for unsorted? Heap just means it's unsorted. It's not in any particular sequence. So we call that a heap. Just the terminology we use for an unsorted bag, if you will. It's a bag is unsorted. Heaps are unsorted. Heaps are, heaps are unsorted. It's a term we use in memory allocation, where if we allocate memory and we don't have a specific order in which we're going to use that memory. Okay, so it's a term we use in computers, in computer programming, but I can understand why you don't know it. It's essentially similar to a heap's data structure, which is an unstructured container, where I can stuff rows of data. That's what a heap file is. Okay. Okay. All right. I'm going to cut this off here and go over to the other meeting. If you have some questions, come see me there.